Right, so in the nephron so far we have done ultrafiltration in the Bowman's capsule. So that's where all the good materials, which are very small, including stuff like urea, glucose, amino acids, water, salts, are all being filtered through into the nephron, and then the filtrate is just carrying on its journey till it gets to the proximal convoluted tubule. This is where we have selective reabsorption taking place. So about 85% of all the materials are reabsorbed back into the blood, and that's make sure that glucose and our amino acids don't end up going down off to the bladder and being lost from the body. Some water is also absorbed there as well, but the major part where water is absorbed is down here with the loop of Henle. So stage 3 is all about absorbing water in the loop of Henle. So let's get on to that. So reabsorption of water. Okay, so it actually involves a few tubes. So it's the loop of Henle and also the collecting duct. So let's just draw those out. So reabsorption of water in the collecting duct. Okay, so your loop of Henle, structure-wise, has the descending loop a little bit thinner wall than the ascending loop. And the reason why is because the ascending loop has got lots of active pumps in the wall of that. So I'll just draw that as we go. So we've got the descending limb of the loop of Henle. And then the ascending limb is much thicker walled. Then we have the distal convoluted tubule, which doesn't really take part in this process. And then the collecting duct. So descending loop of Henle, because the materials are going this way, ascending loop of Henle, because the materials are going up, and then we have the collecting duct. Right, now let's pop in some of the molecules which you're going to find in the filtrate at this stage. So you're going to find lots of water, so let's just pop some water in there everywhere. So in the filtrate, popping water in there. Lots of water, so as a little key, that blob is water. Then there are lots of salts. So for salts, I'm just going to put the words like sodium ions and chloride ions in there. So I'll use this pen maybe. So there's some sodium, chloride, sodium, chloride, sodium, chloride, etc. So this is all in the filtrate. Just going to pop it all in there. Now I'm not going to bother necessarily to put stuff like urea in there, because actually you can take it as read that this urea isn't going to change now it's in the filtrate. It's going to carry on until it goes off to the bladder. Right, so I've got sodiums, and the other salts would be our chloride ions. So often that's just referred to as salts. Okay, right, so in the filtrate then, waters and some salts, and urea, which we're going to lose. But we're talking about the reabsorption of water here. So how does it happen? So remember, the whole of these tubes are covered by the capillaries, so they're close to the bloodstream. And the idea is that what we want to do is create a very, very low water potential down the bottom of these tubes in the medulla, so that the water will be drawn out from the collecting duct into the capillaries by osmosis. So that's kind of like the whole purpose of this, is that what we want to create a low water potential in the medulla, so that we can get water moving out of the collecting duct into the capillary. So how is this going to happen? Right, now I would probably say to you, ignore your textbook that we've given you for the time being, because I think it actually makes it look a little bit more confusing than it needs to be. But there are some things that you do need to know about these tubes before we go any further. So this particular wall, the ascending loop of Henle, is impermeable, so doesn't let, impermeable to water. So the walls of this particular ascending loop of Henle do not let water through it, and the walls of the descending limb have got very low permeability. to salts. So very low permeabilities, things like sodium ions or chloride ions, moving into them or out of them. So it's important to know that before we set off on our journey. Now we can start anywhere because it is actually a circle or loop that's going to take place. But to me, what makes sense would be to start to look up here in the ascending loop of Henle and start to look at this wall here. Now this wall we said was much thicker than the descending loop of Henle, and the reason for that is there has to be space for active pumps. So there are active pumps in the ascending limb, got some on this side too, and these active pumps are able to move sodium ions and chloride ions, into the medulla. And chloride ions and sodium ions. So they're active pumps, active transport. Okay, so these pumps are active transport pumps to put sodium and chloride ions into the medulla. Now, as a consequence of those ions being in place, what will happen to the water potential in this area is that it will become a much lower water potential. So when the ions are actively pumped into the medulla, we get a low water potential in the medulla region. Now, as a consequence of that, water will be drawn out from the descending limb of the loop of Henle by osmosis. So we know that this wall can allow water out. So water can move simply out by osmosis into the medulla. And as this happens, what happens to the filtrate as it's losing water is we can see that it becomes a lot more concentrated. Because as you're drawing water out of it, those ions are becoming more concentrated in that area because there's less water to dilute them down. Now, towards the base of this loop of Henle, this area down here is permeable to ions. So as they're starting to build up in a high concentration, these ions will diffuse into the medulla and cause a very, very low, water potential in this area. So there'll be lots of diffusion of ions taking place, and this will occur until an equilibrium is reached. So there'll be lots and lots of ions in these areas, causing a really, really low, so very low water potential in this area. So water will then be drawn out from the collecting duct by osmosis into the medulla and into the surrounding capillaries. So surrounding capillaries, well, water will move into them, H2O, will simply move into those capillaries by osmosis. So just by those simple processes mentioned, we've been able to get water reabsorbed into the capillaries by osmosis. So let's just look at it step by step. You can look at your book, but I do think it makes it a little bit confusing. And now I'm looking back at my drawing, I'm thinking my drawing's not that great either. But the stages that make sense to me in the order I would begin with is to understand that these walls here do not let water out, so low impermeability to water. The collecting duct is very permeable to water, so you can say permeable to water. It's got high permeability to water. Ions can move into this tube here, but it's a low permeability, so I would say very low permeability to salts, if at all. So down the bottom we do have high permeability area for salts. So I wonder if I could draw this out a bit tidier now we've got the full drawing. Let's see if I've got an extra piece of paper. Yes, I have. So just to kind of recap some of those things, we have got our tube. Much thicker on the ascending. Proximal convoluted tubule is to do with balancing out ions and the hormones, but we don't cover that so much in our course. So if you're going to draw this from scratch, what I'd probably suggest you start off by saying is this wall here, the ascending limb, has got a low, or no, sorry, It's completely impermeable to water. This wall is permeable to water, but it's a very low permeability for salts. The bottom bit here is permeable to salts, and the wall up here is also permeable to salts. The collecting duct is very permeable to water, and we're in the medulla actually, so at the moment we've got to the proximal convoluted tubules. They're at the top, those are the cortex, and this is everything below here is the medulla. And what we said before is that we're trying to get this idea of water moving into the medulla and then going into the capillaries which are surrounding it. So the moment the water comes out of your nephron tube into the medulla, it will then move into the capillaries to get taken away. So the idea is that we're going to create an environment where water is drawn out by osmosis, then water will move into the capillary to get taken away. So the stages that we had was an active pump, which was going to actively pump out salts into the medulla. So we're always going to maintain a salty medulla. That's happening on both sides. So we've got sodiums and chlorides there. Okay, some more there. So we've got a salty medulla occurring. As that is starting to get a lower water potential compared to the filtrate coming down here, then water moves out of the descending limb. This water will move out by osmosis into the medulla, and as a consequence we start to get a build-up of salts, which before was diluted down, and these salts will then, in the area where it's permeable to salts, start to diffuse out into the medulla. So we start to create a very low water potential down the bottom of this loop of Henle. So around this whole area is a very low water potential, and as a consequence then water will be drawn from your loop of Henle out by osmosis into your bloodstream, and it's taken away. So that is how you reabsorb water at the loop of Henle. Now, some organisms, say for example the kangaroo rat, have extremely long loop of Henles, and the idea being is that will give them the maximum surface area to create this salty medulla to allow water to be absorbed in the collecting duct. There are some other terms that we should also know with this. So we have here a system which is called the countercurrent. Just write this. Countercurrent loop multiplier. Right, so what does that term mean? So first of all, the countercurrent is straightforward because you've got fluids going down one direction and then going up the other, so they are countercurrent to each other, so going down, going up. Then you have a loop because it is this hairpin bend here, and then you also have the multiplier part of it. So what the multiplier is all about is that you are increasing, you're multiplying the water potential, you're multiplying the saltiness of the medulla down the bottom. So you're actually multiplying the saltiness of this area, so you're making it far lower water potential than it originally was by moving the salts into the area. So sometimes it's called a hairpin countercurrent multiplier. And yeah, hairpin bend here that you're getting. If you ever watch racing of racing cars, often you have come into a hairpin bend it means it's a really tight bend before the road goes back up. So sometimes it's called a countercurrent loop multiplier, sometimes it's called a hairpin countercurrent multiplier, but it's all to do with the direction of the fluid, so countercurrent. It might also mention hairpin if it's talking about this very tight, close bend. And the reason why it's a hairpin bend is because then you can have the ascending limb very close to your descending limb. The multiplier is all about multiplying the saltiness of the medulla. So you're decreasing the water potential quite dramatically in that area. And I think that's everything you need to know. Students sometimes find this hard, so what I would do is always start here. Always start with that active pump. Then think, okay, active pump moving salts into this area, what's it going to do to the water potential? What's then going to happen to do with the water? If water's being drawn out, what will then happen to the salts? Well, they're going to become more concentrated, so they're going to diffuse out. What's then going to happen to the medulla if salts are everywhere down here? It's going to create a very, very low water potential in that area. So therefore, what will happen to the water which is in the collecting duct? It will get drawn out by osmosis and then move into the capillaries surrounding it. Marvellous. So any questions, please do ask.